So we're gonna do some more algebra today. Surprise. I want to start with what we were talking about last time on the worksheet that we did. There are solutions to that up on Blackboard as well in the group work section. And I want to tie the ideas to what we're going to talk about in chapter 6, which is something called solvable by radicals. So we're in chapter 6. We're going to look at solvable by radicals, which is the idea that's the theme of the chapter. One of the examples on the worksheet that we were looking at, I think it was S was a plus b square root of 2, where a and b were rational. We knew it was a subset of the complex numbers. And I'm pretty sure everybody got through showing that it was indeed a subfield using the subfield theorem. So S is a subfield of C. Use that subfield theorem. So you showed that it had at least 2 elements. It's cool, 0 and 1 are in there. That it's closed under addition and multiplication, and that you have additive inverses. And for non-zero things, you have multiplicative inverses. That's what the subfield theorem says. There was a second part of that. I guess I should say use subfield theorem. There was a second part of that question that said any field F that contains the rational numbers and the roots of x squared minus 2 also contains S. We're going to talk about that. We'll give a quick argument to show why that's true. But I want to connect this idea to some notation that's going to come up in class today and for the rest of the course. So we'll come back to that. But before we show that's true. So if I take a polynomial and I make it a superscript of something, this looks very weird. I'm not saying take the set of rational numbers and raise it to that power. This is going to be the smallest subfield of the complex numbers that contains Q and the roots of that polynomial. So I can't just take unions. That was one of the big highlights from the worksheet, that, taking unions is almost guaranteed to make the algebra break. So instead we put that stuff together and we're like, okay, put in anything you need from the subfield theorem. So I could think about what's the smallest subfield of the complex numbers that contain the roots of this guy. And I could also write with parentheses Q and then parentheses, maybe I'll literally put in the roots. This is going to be, again, a smallest subfield, the smallest subfield of the complex numbers that contains Q union, in this case, plus or minus 2. And those 2 fields that I wrote down with different notation, one has the polynomial and the superscript and one has parentheses and some stuff. I hope it's pretty reasonable to believe those fields are equal. Those literally are the roots of x squared minus 2. I'm tempted, I think I learned this from one of my graduate advisors. I'd go through great detail to prove something in my dissertation, and he'd just write duh along the side, the big X, you can take it out. So I too had to learn concision at some point. But yeah, those are the smallest subfield of the complex numbers that contain Q and plus or minus square root of 2. And what I'm saying is that S is that field. And so when I say smallest, I mean that if there's another field that contains Q and that stuff, it has to pull in the smallest subfield. So the claim that we made was that this is also equal to the set S. And this, zoop, I'll give you a little sketch of the argument. So let's suppose F is a subfield of the complex numbers containing Q and then plus or minus square root of 2, the roots of that polynomial. And to show that this contains S, I'm going to pick an arbitrary element of S and show that's an element of F. So let A, B, and Q, sorry, A and B are Q, so that A plus B square root of 2 is an S. Well, what do we know? We know that A and B and square root of 2 are an F by assumption. And F is a field, so it's closed under addition and multiplication. And therefore, since I build A plus B square root of 2 with multiplication and addition, I get that that's an F. So S is contained in the field F. So in general, if you're trying to show something as the smallest subfield, you're like, okay, pick any other field that does the same thing and show the one that's supposed to be smallest lives in that field. All right, any questions so far? The notation's a little bit weird. I'll make another claim and let's see if you believe this claim. So back to our example, I had the positive square root of 2, the negative square root of 2, and I'm going to make the bold claim that that's Q, and all I need to throw in is the square root of 2. Do you buy it? This is where there's a little bit of a magic wand element happening. On the right side, Q adjoin the square root of 2, I'm saying it is a field. I'm just declaring it to be a field that has the rational numbers and square root of 2. And once I know it's a field, I know that additive inverses have to be in there, which means negative 2 also, just by the magic wand aspect of I said it's a field, gets pulled in there. So these are the same fields. Even though negative square root of 2 isn't in Q, it's the additive inverse of something in Q with those parentheses and square root of 2. So this is because square root of 2 and its inverse, its additive inverse, are in Q parentheses square root of 2. Okay, so I want to do a couple more. Let me tell you how to name these things first. Let me do a remark. So when we say in algebra, A is the smallest blank, satisfying blank, we mean any other blank, satisfying blank, contains A. It's like a very weird and probably kind of boring math mad lib, but the first blank is, we could talk about any algebraic object. So for us, we're talking about fields right now, but in linear algebra, you could be talking about a vector space. Maybe you're satisfying some algebraic property. then any other of the same type of algebraic object satisfying the same algebraic property contains A. Kind of like the smallest way you can make the algebra work. Any other set where the algebra works has to contain this thing you built. So what we just did was we talked about the smallest field satisfying some stuff is in the field. This is a very vague definition, but this is really what we're doing. So any other field that has the same stuff in it has to contain our smallest subfield. I don't know if you would have talked about it this way, but another example is the span of a set of vectors. So if you have like 6 vectors, they themselves are not a vector space, but their span is a vector space. And it will be the smallest vector space containing those 6 vectors. Meaning any other vector space that contains those has to contain the span. And eventually we'll get more types of objects in this class. We'll talk about rings and groups, and we'll have the same idea of smallest stuff there. All right. So far, so good? Yeah, Daniel. This stuff is in it. Yeah, like for us, it's like it contains some stuff. Sorry, I have a hybrid cursive handwriting sometimes. All right, so let me give you a definition so that this notation is kind of pinned down for us. I'm gonna let F be a subfield of the complex numbers. And I'm gonna let R1 through Rn be elements of the complex numbers. The smallest subfield of the complex numbers containing the union F and the set of all the R's. So that's what we're defining, is denoted F with the R's and parentheses following it. And called the subfield generated by F and the R's. Or sometimes you'll hear it called, and I'll probably say this a lot because this is how I learned it, F adjoin R1 through Rn. So the adjoin is like throw in R1 through Rn and then make it a field. So that's the kind of set we were just talking about. We were talking about the rationals Q adjoin square root of 2. Or the rationals Q adjoin the roots of some polynomial. So if I write F with a P of X up top means F adjoin the roots of the polynomial P of X. And this usually, we want the coefficients of P of X. So the stuff attached to the X's to come from the field F. So I've already used this notation a little bit, but now here's the definition, and this is how the book will talk about it. All right. So there's kind of this like scale of abstraction that goes along with this. I could talk about, and usually we're starting in Q. Talk about Q adjoin the roots of a polynomial, and that's very abstract. We might not even know what the roots are. We're just saying like make a field that has the rationals and whatever those roots are, they're going to be in there. And one of the things we started the course with was, I claimed that we're not going to be able to have a nice algebraic formula for the roots of an arbitrary degree 5 polynomial. So if like that's one of those polynomials, then I can talk about this in the abstract, but I can't actually necessarily tell you what the roots are. So super abstract. On like the most concrete side, we could have a set like S, which is going to be like specific elements. Right? I kind of tell you how to build those specific elements. So there it was like a plus b square root of 2. I know exactly what an element looks like. And that's the most concrete we can get. So we know what an arbitrary element looks like. We know how to write down an arbitrary element. And so that's kind of like, I would prefer to be on that end of the scale when I can, because that's way more useful. I can actually do stuff with the arbitrary elements. And there are like kind of these pit stops along the way. Like you could also get to Q adjoin some R's. Well, I don't know necessarily what an arbitrary element looks like, but at least I know the things I'm adjoining. Like maybe I couldn't find the roots of P of X, but maybe I can throw in some R's, and now at least I know those specific R's are in there. So I'd say this is still like, if this is kind of the middle, I'd say the Q adjoining the R's is still kind of on the abstract side, but it's a little bit more concrete. You can at least point to like, here are the non-rational building blocks that I'm going to use. And so we're going to kind of live in this space for a while, which will be uncomfortable because I think we all prefer when things are more on the concrete side. But we're going to move to this side. We start to see how to write down specific elements for things like Q adjoin the R's or Q adjoin P of X in chapters 10 and 12. Chapter 10 takes a view that's sort of based on some polynomials, and then chapter 12 takes the same view, but it's like, but guess what? We can use linear algebra. So we won't get there till after spring break, but just there we'll get some linear algebra. Now, I am a professional mathematician, so I am so pumped whenever linear algebra shows up, because there are like 2.5 theorems in linear algebra. There's rank nullity, that those dimensions add up nicely. There's a square matrix is invertible if and only if, and then like 20 billion things. And then there's the idea that vector space dimension is well defined. So we're going to use the dimension of a vector space to help us figure out like, how do we write down these elements in a nice way as a preview of coming attractions. But until we build up like all of that algebraic machinery, we're going to kind of be stuck on the abstract side. In very specific cases, we might be able to figure out what S is, like we did on the worksheet. Just putting that out there. So if you feel like a little bit like on non-solid ground, that's okay. It isn't, we'll make it more solid, but I acknowledge your feelings are valid. And this is my attempt at empathy. I should read more parenting books. They're very helpful. There's a lot of language you can use that sounds empathetic, even if you don't feel it, which is great when it's 3 a.m. and your toddler is losing his mind. Like, that sounds rough, buddy. I don't believe it in my heart, but you think I do. Okay. I believe everything in my heart that I say to you all, of course. Never just be faking empathy. All right, let's do a couple examples of these, and then we'll get to the kind of big idea for today. Let's see. From our worksheet, we have a few examples. I think you probably, hopefully you believe, well, let's mess around with this one. what are the fourth roots of unity? That's what that polynomial is about. Paul, I see it on your face, kind of, or Anson. Oh, you're giving me like the nicknames. Anson's already jumped ahead to like, we already know these guys by their cute names. They have formal names too, like when they're graduating and you call it their formal names, it's zeta 4 squared, zeta 4 cubed. But yeah, it's going to be plus or minus I plus or minus 1. So let's write them out formally first. Zeta 4 squared, zeta 4 cubed, zeta 4 to the fourth, or zeta 4 to the 0. We could do, like, we could write that list down without hopefully thinking too hard for any x to the n minus 1. We just have the nth roots of unity. And in this case, it's pretty nice because if we think about it, even just sort of the geometric picture, we're just going a quarter of the way around the unit circle. That means we hit the axes as we go. So this is going to be q I, -1, -I, and 1. All right, I claim I can pretty quickly toss 2 of those out. Yeah. Yeah, -1 and 1 are already in Q, so I'm going to ditch those. So now I'm left with plus or minus I. And so from here to here, I've got plus or minus 1 are already in Q. So I don't need to throw them in separately. And I also claim I can throw out -I. And that's because it's the additive inverse of I. So if I'm making a field that involves I, -I is automatically going to have to be in there. I don't need to write it out. So once I is in a field, its additive inverse must be 2. And then we could do an argument really similar to what we did before with a plus b square root of 2, and we could write this down. I think on the worksheet I called it T, which was a plus bi, where a and b are in Q. And I'm going to circle that equality in green. That would be the argument where I say, okay, any field that contains the rationals in I is going to have to contain T. And that's how I make the argument that that really is what the smallest one is. So I need to prove T is the smallest subfield of C containing Q union I. Once I do that, the notation for that field is Q adjoin I. So that's how I know that those would be the same. So that's a little bit that connects this new notation to stuff we've thought a little bit about on the worksheet. All right, let's do more examples. Oops, sorry. Here's one example. Here's another example. Okay, Q adjoin the roots of x minus 1. How many roots does it have? 1. It's degree 1. Fundamental theorem of algebra says there can be at most 1. And we can read it right off. It's Q adjoin 1. Okay, well, that's just Q. So sometimes you put a polynomial up there, but it's actually not that exciting. Like if I did x squared minus 1, it looks like it might be complicated, but in this case, it's Q adjoin plus or minus 1, and both of those are rational. So that's also Q. So we don't always actually end up adding anything depending on what the roots are. I could look at an arbitrary degree 2 polynomial, and I guess I should be careful that a is not 0 here. Maybe it would be okay if it was 0. I know from the quadratic formula that most of the stuff is going to be rational pieces. There's only one thing that might not be rational. And so I claim that this is going to work out to be that square root of b squared minus 4ac. And then all the other pieces of the quadratic formula, oops, sorry, I don't know why that erased. All the other pieces of the quadratic formula come from adding, multiplying, or dividing by non-zero rational numbers. So the only thing that's definite that, well, I guess might not be in Q, depending on what A, B, and C are, is that square root thing. And so if b squared minus 4ac is not the square of something rational, that's going to be some new real or complex number that we've got to put in there. So this is in general. So quadratic polynomials are nice. We could kind of do the same thing for degree 3 or degree 4 polynomials by figuring out what their formulas look like and figuring out what's the stuff that's not already in Q that we have to throw in. And there's one more example that we talked about on the worksheet. We looked at Q adjoin the roots of x cubed minus 1. And so if we're going straight from the definition, we know that's going to be Q adjoin 1, zeta 3, and zeta 3 squared. Once I know I can throw out 1. And once I have zeta 3 in there, it's closed under multiplication. So zeta 3 squared will also have to be in there. Since zeta 3 squared is zeta 3 times zeta 3. And I'm closed under multiplication. And then you were kind of messing around with a little bit on the third page of the worksheet. You're sort of narrowing down what the smallest subfield might be. And it's true that this is going to end up being the set that looks like A plus B zeta 3, where A and B are rational. And one of the ways we work with this equality is we remember that zeta 3 is a solution to x squared plus x plus 1 equals 0. And if we plug zeta 3 in and then solve for zeta 3 squared, that tells us, oh, we can rewrite zeta 3 squared as a rational thing, plus negative 1, another rational thing, times zeta 3. So that tells us that zeta 3 squared is actually in that set as well. We'd have to prove it's a field to get the inverse and all that good stuff, but this is not going to be so much the focus of what we do. Like, I'd sort of think of this example as better for chapter 10 or 12, where we start figuring out how do we use relevant polynomials to help us out. And I guess I feel compelled to give you one warning as well, which is that not everything ends up being A plus B, something irrational. From all the examples we did, you might guess that, but Q adjoin the cube root of 11 is not going to be equal to A plus B cube root of 11. Because it's not going to be closed under multiplication. I think cube root of 11 squared is not going to be able to be written as A plus B cube root of 11. So later, we'll figure out that we can write it in a different way, and that actually we need A plus B cube root of 11 plus C cube root of 11 squared. And so as we get weirder and weirder things that we're throwing in, it gets more complicated to figure out what the elements actually look like, which is why we actually do all the stuff that leads up to chapter 10. Anyway, I just didn't want you to think everything just looked like A plus B blah. All right. That's a pretty good sequence of examples leading up to our next thing. I want to give you a little bit of context. I'm going to tie this back to the beginning of the course. So I claimed there's no formula for the roots of an arbitrary degree 5 polynomial involving algebraic operations, algebraic steps. I want to kind of break that down a little bit because I want to think about how to use the stuff we've been developing to imagine that. When I say algebraic operations, I'm talking about addition, multiplication, the inverse operations of those, the inverses, so like subtraction, and you can think about it as division, kind of for shorthand. Maybe I need some nth powers. And maybe I need some nth roots. Like in the quadratic formula, I'm going to need some square roots. So those are all algebraic operations that I'm thinking as like legal things I can do to build a nice algebraic formula. Sound good so far? And if I think about what happens in a field, most of those things are guaranteed to be things that I can do in a field, like addition and multiplication and inverses for those operations. And then if I think of nth powers as repeated multiplication, these all happen in a field. Right, like once I've got some elements in my field, I know I can add, multiply, subtract, multiply by the multiplicative inverse, or get nth powers of those things. So like that part of the idea of algebraic operations is related to being in a field. And it's the nth roots that are like the extra sauce, like the square root of something might become irrational or even complex and not real anymore. And that's where I want to be able to also put in nth roots of things that start out rational. So this is the extra stuff. Like in the quadratic formula, b squared minus 4ac is nice. But then I want to be able to take the square root of it. And that's maybe not so nice. So that's when I say nth roots, I mean being able to take nth roots of things that were nice to start with, but now they look a little complicated because we've got some roots in there. So what the next definition, and it's a bit of a doozy, just to warn you, is all about is taking this idea of like nice algebraic formulas for roots of polynomials and turning it into something about fields, nth roots, and then how you can build stuff from nth roots and good elements. So just keep in mind, it's all to try to get a good solid mathematical footing for the question we're trying to ask. Okay, give yourself a second and just like take stretch break, just like mentally get ready. Deep breath in. It's a lot. This one, it takes a little while to get this next one under, like in, I don't know, like tattooed on your heart, I guess, if that makes sense. I'm going to give you lots of examples to work with. It's okay if it doesn't immediately sink in. It took me plenty of time to absorb this as well. It's just, it's a weird thing and you have to play with it and practice it. So if it feels frustrating, that's normal and expected. It means you're learning. If nothing in this class felt frustrating or hard, then you probably didn't need to take it. I'm sorry I'm wasting your time, but I think I'm not wasting your time. Okay. So this is the big one. This is the definition of solvable by radicals. And this word radicals, you can think of as meaning nth roots of stuff. All right, get my we're going to start with, I'm going to let F be a subfield of complex numbers. We could do this with different sort of fields sitting up at the top. If we did it over, well, we've got lots of different types of fields. If we did it over certain types of fields, we'd be doing number theory. If we did other types of fields, we'd be doing physics. For us, the complex numbers are really nice. So we're going to stick to the complex numbers. We've got a subfield of C, and we say the polynomial P of X with coefficients from F. And I think Bob starts using the shorthand for polynomials with coefficients from F. He'll use F and then he'll put a square bracket with the X. So that's saying we've got a variable X in the square bracket. We're taking powers of that and then multiplying by coefficients from the field F. It's like a shorthand for polynomials. So we've got this polynomial with coefficients from F. We're going to say it's solvable by radicals over F. Provided a few things happen. Well, we want some elements of our big field C that's kind of sitting up there overseeing all of this. So R1 through Rm and C, and positive integers. K1 through Km, each one gets paired up with an R eventually. Satisfying two things. All right, so the first thing that we want to satisfy is that if I take that first R1, oh, sorry. No, I'm a little out of order. Okay, so if I take F and I adjoin the roots of P of X, that's going to be contained in F adjoin these R's. And I want to note here that usually or often these R's that I'm throwing in are not the roots of P of X. Like they are in some special cases, but just better to think of them as they're like building blocks, but they're not themselves necessarily the roots of P of X. And that's because of the next thing I'm going to make them satisfy. So if I look at R1 and I raise it to some power, it's going to belong to F. And then I'm going to do some stuff with the other R's. But you could think about this as like, I is not in Q, but I squared is -1, which is in Q. And so I might be one of these R's because I can square it and I can land it in that field. All right, so they're things that aren't necessarily in F, but they're like nth roots of things that are in F, or K1th roots of things that are in F. And then as I start building things, I want the ith one to be able to be raised to some power, and maybe it's not in F, but it's going to be in F adjoin the previous things that I built. And so in my previous example, if my R1 and the K1 that went with it was 2, so if R1 is I and K1 is 2, then maybe R2 is going to be the cube root of 3 plus I. And if I cube that, that's going to be in Q adjoin I. Because now I've got a 3 and an I. So in this case, K2 would be 3, and then R2 K2 is 3 plus I. It's not in Q, but it's in Q adjoin I, which was the previous thing I threw in. And I'll do some more examples of this. But the idea is you can kind of like build up to the roots of this polynomial by carefully picking out how you're going to put in nth roots of relevant things. And then once you put them in a field, once you put those nth roots in a field, you're allowed to take powers, you're allowed to add, you're allowed to multiply, you're allowed to divide. So all those like legal algebraic operations can happen in that field. And so one way to think about this is like every quadratic degree 2 polynomial is solvable by radicals because we only ever have to worry about R1 being the square root of b squared minus 4ac. And then the k1 that goes with it is 2. And I'm like, cool. So like the roots are going to be built out of the rational numbers and that extra square root. And if you've ever let your eyes glaze over the cube root formula, it's a lot awful. There's a big cube root on the outside, and then I think there's some square roots underneath that cube root. And so that might say, all right, so then I have to put in that square root first because that's like the most nested thing. But then once I have that, I can take cube roots of stuff that involve that square root. So then I can put that big cube root in, and I can kind of build up to the formula in that way. What's kind of crazy is you're saying you can still do that for 4, like the roots of degree 4 polynomials. There's a formula that's out there. It's awful, but it's out there. And you can build up those roots in a kind of systematic way like this. But in general, you can't do it for an arbitrary degree 5 polynomial. Like this is just going to not work. But if you think about the logic of saying something doesn't satisfy this definition, this has a bunch of there exists some R's, there exists some K's. And if you negate that, you have to be arguing that like for all possible choices of R, for all possible choices of K, it's going to fail. And logically that sucks. That's a super hard place to be in logic land. So pretty much every algebraic thing we're going to study in this course was designed to get an equivalent version of this definition that you can actually prove doesn't hold without going through all that horrible for all. So that's where we're going. I want to be conscious of the fact that it's 10:45 and super snowy outside. I will start class on Monday with an example of this definition. I will also, I'm going to post the notes from up to this point in the course. I'll put it in the notes if you want to like put your eyes on it ahead of time before the course. So we'll pick up with solvable by radicals on Monday. I'll also get the homework for Tuesday posted today. Sorry, I just forgot to put it on my to-do list. But yeah, enjoy your Valentine's Day. Stay upright in the snow as much as possible. Yeah.